What is going on, guys? Welcome back. In this video today, we're going to take a look at the most important evaluation metrics for regression when we do machine learning. So let us get right into it. Alright, so we're going to take a look at the most important evaluation metrics for regression in this video today, but before we get right into it, I would like to clarify something that might confuse a couple of beginners, people that are new to machine learning, which is that regression is not necessarily equal to linear regression. Now, linear regression is a type of regression, which is a linear type, but regression is not always having some data points, drawing a line, and then saying, this is my model. Regression is just a task of predicting values that are not class labels, that are not class probabilities, that are not yes or no, but that are on a continuous scale or spectrum. So we're trying to predict continuous values rather than discrete class labels. That's a difference. So for example, if I have an image of a cat, the question, is this an image of a cat or a dog, would be a classification question. Asking how old is the cat would be a regression question, because we're actually trying to predict the age number, the age value. Similar to that, we have house price prediction, insurance premium prediction, stock price prediction, crypto price prediction, whatever. Whenever you're trying to predict an actual value and not just a category or a class, that is regression. And this can be done with a linear regression. This can be done with random forest regression, with support vector regression, with neural networks. So you can have very complicated models predicting stock prices in the industry, but they're still just regression models. But they're not just a line through some points. So for those of you who think that regression is boring, that's not the case. You're probably thinking about linear regression. Now, what I want to do in this video today is I want to compare all the different, or not all, but the most important metrics here. And for this, I have prepared this Jupyter notebook where we have quite a bit of code, some math, some bullet points, comparing different metrics, talking about when to use them, when not to use them, what the problems are. And this is what we're going to do in this video today. Now, you don't need to code along. This code here is mainly exists mainly to show you that our implementation of the formula is equivalent to just calling the function from scikit-learn to see that this is actually how you calculate that. Besides that, it's more of an explanation what the different metrics do. So let us nevertheless take a look at what we're doing here in this notebook. We're loading the California housing dataset, which is a classic dataset for regression. The target variable is the price. This is what we're trying to predict. We're splitting it into a training set and a testing set, and then we create two models, a linear regression model and a random forest regressor. We scale the data, we train the two models, and now what we can do is scikit-learn offers the method called score, which means that we can just call rec.score or forest.score to evaluate the models easily on the test set. And in the case of a classification task, this gives us a value between 0 and 1, which is the accuracy. So 1 would be 100% accuracy, 0 would be 0% accuracy, 0.5 would be 50% accuracy, and it basically tells us how many of the samples were classified correctly. Now, we don't have such a thing for regression because we're not aiming to always predict the exact value. It's more reasonable to get as close to the actual values as possible. So you don't want to have 0% accuracy because you never predict the exact value if you get very close to it. So by default, when you call the score method, you get the R-squared metric, which is the coefficient of determination. Now, this is also a value between 0 and 1, which is why it might be confusing oftentimes when you encounter this for the first time. It's not an accuracy score. It's actually telling us how much percent of the data's variance can be explained by the model. So this means you have the data, you have some variance in the data, and how much percent of that variance can be explained by the model. Now we can take a look at the formula here, and when it comes to the math, you don't need to go deep into it if you don't want to. So I'm going to explain the formulas to some degree in this video today. I'm going to go through the bullet points and all that. If you're just interested in what it does and how it's to be interpreted, you don't have to understand the math necessarily. So you can also just skip the explanation, you can ignore it, you can just listen to it and, not pay attention. But if you're interested, it might make sense to understand what the formula is about. So you can see that this formula here, 1 minus and then two terms. The two terms here are the following. We have the first one, which is the sum of squares of residuals, which is a fancy way of saying just the squared errors, the sum of the squared errors, which means we have the actual value that should have been predicted, yi, and we have y hat I, which is the prediction our model actually made. there's going to be a difference. That difference squared is going to be the squared residual, and then we can sum up all the squares, and we end up with this upper part with the numerator of this fraction here. Now in the bottom part, we have the total sum of squares, which is basically just, or the total sum of squares, basically just the variance of the observed values around their mean, which means you have the actual data points and you have the mean value for y, and then you basically calculate the differences to get the variance. So how far apart are the values from the mean? And when you divide the first term over the second term, or by the second term, you get the percentage of the variance that cannot be explained by the model. So the percentage that is still that is not explainable by the model, and when you take 1 minus that, what you get is of course the opposite, which means that you get the percentage of the variance that can be explained by the model. Now I don't want to go too much into the math here because I want to focus on what this metric tells us and when to use it. But basically this metric has some problems. Now one good thing about the metric is it's easy to interpret. It's between 0 and 1, and the closer I get to 1 the better, the closer I am to 0 the worse. So that's an easy to interpret metric. However, it's not necessarily giving us full information here. First of all, I can artificially inflate it by adding new and new variables, or more and more variables, which are actually not useful, because what's going to happen is when I add more parameters to the model, more values to the model, what usually happens is either nothing, or I'm going to get some increase in the R² score, which means that I can add a ton of features, most of them useless, and I will still increase probably at some point the coefficient of determination, the score here. So this is going to be resolved in the next metric, which is the adjusted R². We're going to talk about this in a second here, but that's one downside. The other one is the model doesn't really, or the metric doesn't really tell us if the model is good or not. It doesn't tell us if the model performs well or not. So for a certain task, we might want to have a certain actual number of how far apart the predictions are. This metric doesn't tell us that. It only tells us how much of the variance it explains. The variance can still be huge. So it doesn't mean that this model is really good just because we get a very high R² score. But of course, it's a useful metric. And also, it's more suited for linear models. So you should not necessarily use this for neural networks or for random forest regressors or any nonlinear models. You should use this for linear models in combination with other metrics, which is also true for the adjusted R². We're going to talk about this in a second, but here you can see that we can calculate this manually. We can just calculate the upper part, the lower part, and then 1 minus the fraction. This will give us the exact same scores as we get from the score function. This is exactly how this is calculated, as you can see. So the adjusted R², I'm not going to talk about the formula too much here, but you can see that here in the denominator we have the number of parameters, or the number of predictors. So the more variables you add, the more you subtract here in the denominator, which means you're penalizing unnecessary complexity. Every new term, every new variable, every new parameter that you introduce to the model is going to result initially in a lower adjusted R² score, unless you can explain more of the variance. So you still want to explain more of the variance, but if you're just adding variables that don't explain much of the variance, you're going to actually decrease the score. So you're penalizing unnecessary variables, unnecessary complexity. And so because of that, we also want to use this metric when comparing models with a different number of variables or parameters, because it takes that into account. And similar to R², we want to use this in combination with other metrics. We want to use this primarily for linear models and in combination with other metrics because it gives us the full picture. This metric alone doesn't tell us anything about the magnitude of the error. It only tells us how much we can explain with our model adjusted for the number of parameters. Now, when it comes to the implementation, scikit-learn doesn't have a function for the adjusted R², so we have nothing to compare it against, but this is how you implement this, and you can see it's basically, in this case, almost the same as the R² score, but it will be different if you add useless variables, so it will go down, and that's the main reason to use it. Next up, we have the MSE and the RMSE, so the mean squared error and the root mean squared error. The RMSE is just the square root of the MSE, And the formula is already in the name. You take the mean, so 1 over n times the sum, which is the mean. N is the number of instances. The mean of the squared errors, so of the squared differences. We have the actual value minus the predicted value, squaring that, summing that up, and then dividing it by n. This gives us the mean squared error, and the root mean squared error is just the square root of the same thing. So these two metrics, I would say, are the go-to metrics when it comes to evaluating the loss of the, or the error of the regression model. The MSE is more useful for optimization because it is differentiable. It's very convenient to take the derivative of it, and it's very easy to do that, which means it's easier and more convenient when it comes to backpropagation, gradient descent, and so on. So for actual optimization in the computer, and the RMSE is more interpretable, more intuitive for humans because it has the same unit as the target variable. Because of course what we do here is we square the differences and then we take the mean, but we have now some magnitude that is not actually in dollars. For example, if our data is in dollars, it's in some squared dollars metric, whereas here, since we're taking the square root, we have the same units as the response variables. So I would say that the only reason to choose the MSE over the RMSE is because it's differentiable and better for optimization. Besides that, both of these metrics are useful when trying to minimize the overall error in the model. They are, of course, sensitive to outliers and to large errors because they're squaring the error terms. This is something that you need to consider. There are other metrics that are more robust when it comes to that. But these are, I would say, very... these are like the go-to metrics. So this one for optimization, this one also oftentimes for optimization, but also for just the interpretability and the intuition of humans. And we can also see when I call the function mean squared error from scikit-learn.metrics that this gives me the same result basically, except for the last decimal places, as applying the formula that we just discussed. So we get the same results here, and this is also the case, of course, for the RMSE. There you go, root mean squared error produces the same output. All right, so next up we have the mean absolute error. So what do we do here? Again, the name tells us what the formula looks like. Mean stays the same, absolute error. We don't square anything, we don't take the square root of anything, we just take the error and take the absolute value of the error, which makes sense, of course. You always want to make sure that you don't have different signs because they would cancel each other out. You know, one prediction has 100 more than it should have, the other one has 100 less, so now my error is 0 if I don't use anything like that. Squaring the values, squaring the error terms, of course, also makes them positive, but I can also do that here with the mean absolute error. And the nice effect of that is that I again have the same units as a target variable, so I stay in dollars, for example. And this metric tells me basically on average how wrong is my prediction. And I'm not squaring anything here, which means that I'm not influenced by large errors as heavily as the MSE or the RMSE. But basically, this is what I wrote down here. The question that we're, or the statement that we're making with this metric is, on average, our model misses the correct value by X. So if you're interested in that, this is a good metric to use here. Now, the problem with this metric is it's not differentiable at 0, which is bad for optimization. So this is not necessarily the best thing to choose for as a loss function for the optimization algorithm, but it's a nice evaluation function that just tells us how wrong we are on average in the original units. So how many dollars on average do I miss the housing value? Now, you will say that these values here are not dollar values. The only reason that we have these 0 point something values all the time is because we're using the scalar here. So we're scaling the data, which of course means that we're no longer having the original units. We don't have dollars or years anymore. We have now some values on a smaller scale. Of course, you can scale them back to get your answer, but this is a very useful metric if you are interested in this. If you want to say something like this, on average, our model misses the correct value by X dollars, X years, and so on. Now, the next metric does almost the same thing. The MAPE, the mean absolute percentage error, it's the same formula, just that we have this division now by yi, so it's exactly the same as before, just that we have this denominator now, and this makes it a percentage. So now we don't have the actual unit, we don't have X dollars and X years or anything like that, but we have on average how much error or how much is my model off in terms of a percentage. And this makes it more interpretable oftentimes, but also more useful when it comes to comparing it with other data sets or across data sets, because then it doesn't really matter what the unit is and what the scale is. It's about the percentage. So that is maybe useful if you want to compare across different data sets. You have the same problem, of course, with the differentiability. So that doesn't go away. And again, we have here mean absolute error, we have mean absolute percentage error, same results here, same results here. And then we also have the median absolute error, which is basically also the same idea, but instead of taking the average, we take the median values. So here now I have this other notation where we have all of the errors at once, then we take the absolute value of them, and then we apply the median, meaning that we take the center value. Now, of course, this is much more robust when it comes to outliers, but in general, it doesn't really capture any effects of large errors or of outliers. It is really not sensitive to the error distribution because it doesn't really matter what's happening left and right. The important thing is what's in the center. What's in the center is my typical magnitude of error, and that's what I'm interested in. That's what I'm getting here with the median absolute error, but I'm not really understanding anything about the error distribution. Maybe there's some huge error that I'm not seeing because I'm just looking at the median absolute error. So that is, of course, a blind spot, but it's much more robust to outliers. It gives us a typical magnitude of error. So here again, median absolute error, just applying the median function, the abs function, onto the differences, onto the errors, and then I get the exact same score. Now, last but not least, these I would say are the most important metrics that I explained here in this video, but last but not least, I have some honorable mentions for those of you who want to look into more metrics. So we have the mean squared logarithmic error, the root mean squared logarithmic error, the explained variance score, the symmetric mean absolute percentage error, the Huber loss, and the two information criteria AIC and BIC. You can look them up if you want to. I didn't want to include too many metrics here because yeah, maybe people will be, will have a little bit of an information overload here. But to summarize it, the R squared gives you the percentage of variance that can be explained, the percentage of the variance in the data that can be explained by the model. The adjusted R squared adjusts for the number of parameters, so it penalizes unnecessary complexity, unnecessary variables. The MSE is good for optimization in general to reduce the overall error. The RMSE is a version that is more interpretable for, or easier to interpret for humans, more intuitive for humans because it has the same unit as a target variable. The mean absolute error gives us the statement, on average, our model misses the correct value by X units, whatever the units are, dollars, days, years, whatever. Then we have the mean absolute percentage error, which gives us the same information as a percentage, not as an absolute value. And then we have the median, which gives us the typical error. So not the mean error, not the average, not considering all the values, but just the center at the distribution, at the center of the distribution. What is my typical error? So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you for watching, see you in the next video, and bye.